Imagine standing beneath a vast night sky, each star shimmering like a beacon of infinite possibility. It's a breathtaking sight, isn't it? That moment when you look up and realize those tiny specks of light are not just stars, but entire galaxies, each filled with billions of stars, planets, and who knows what else. Our universe is vast, mysterious, and always leaves us wanting to know more. What if the answers to our greatest questions lie somewhere out there, hidden among those dazzling points of light? What if the mysteries of our existence, of time, space, and reality itself are waiting to be uncovered, silently swirling amidst the cosmic dust? The universe has always been a playground of wonder and discovery. For centuries, humanity has sought to understand its workings, uncover its truths, and map its vastness. Our understanding has come a long way, from ancient civilizations observing the stars to groundbreaking theories like Einstein's relativity and quantum mechanics, which challenged everything we thought we knew. But here's the thing, with every answer we uncover, the universe throws us more questions, more enigmas, and more puzzles that leave even the most brilliant minds baffled. Among the stars, anomalies take shape, strange phenomena that defy the very laws we've established to understand reality. They are the whispers of something greater, something unknown. Think about it. We are cosmic detectives, trying to piece together the story of the universe using light that has traveled billions of years to reach us. Telescopes become our magnifying glasses, and data becomes our clues. Every star, planet, and galaxy holds a chapter of this grand saga. But the kicker? For every chapter we read, 100 more seem to appear. Why do some stars mysteriously disappear without a trace? Could something, an unseen, incomprehensible force, be sculpting the structures of the universe? For every anomaly we discover, another puzzle arises, each piece begging us to push further and look deeper. Our universe is a theater of extremes. Black holes lurk as cosmic devourers, swallowing everything, light, time, even space, into an abyss from which nothing escapes. Pulsars spin as celestial lighthouses, emitting beams of energy that sweep across the cosmos like a beacon. Quasars, blazing brighter than galaxies, serve as distant reminders of unimaginable power. But then there are the quieter players, the ones that don't scream for attention. Rogue planets silently drift through space, unanchored to any star. Entire galaxies remain cloaked in mystery, their stars seemingly missing. And then there's the faint echoes, signals that seem to originate from points beyond imagination. Are they natural or the work of something more? Our tools, as incredible as they are, only give us glimpses. Telescopes, satellites, and complex theoretical models are like flashlights in a vast, dark mansion. They illuminate fragments of rooms, but the mansion itself remains concealed in shadows. Staring out into the cosmos, it's humbling to think that we are just tiny observers on a pale blue dot, decoding what little we can from our vantage point. The universe is limitless, yet we perceive only a fraction of it. This humbling realization that for all we know, the unknown vastly outpaces it, shapes every step of our exploration. The anomalies we uncover challenge more than just scientific thought. They push us to ask deeper questions about our place in the universe. What does it mean to exist in a cosmos so vast, so ancient, and so full of unknowns? Every unsolved mystery doesn't stop us. It inspires us to keep going, exploring, and learning. It's not a barrier, but a spark that keeps the flame of discovery alive. Each unanswered question is a reminder of humanity's relentless curiosity and the power of wonder. And the mysteries don't end. Strange signals reach us from the vast interstellar void, their origins unknown, their purpose unclear. Celestial objects behave in ways that seem to defy the laws of physics. Invisible forces shape galaxies into grand structures far beyond our comprehension. Could these phenomena be clues to a deeper reality, one we've barely scratched the surface of? Or are they simply quirks, fleeting glitches in the cosmic tapestry that tease dimensions we cannot perceive? The universe keeps its secrets well, tantalizing us with glimpses of its grandeur and always keeping the full picture just out of reach. But that's the beauty, isn't it? The pursuit of these answers, the thrill of uncovering one piece of the puzzle only to find the puzzle much bigger than we thought, is the heartbeat of discovery. And as the universe continues to expand, so does our ambition to understand it. Chapter 1: CMB, the Axis of Evil. The cosmic microwave background, or CMB, carries whispers of the universe's beginnings. Its faint glow left behind from the Big Bang, a thermal radiation dating back nearly 13.8 billion years. Through its study, scientists have unlocked key pieces of the puzzle about how our universe began and evolved into the vast expanse we observe today. But there's always more to uncover, and within the CMB lies a perplexing anomaly that has sparked debates and theories for years. Known as the Axis of Evil, this anomaly has challenged long-held assumptions about the structure and isotropy of the universe. To understand it, we need to revisit what the CMB tells us. Typically, the CMB is consistent and uniform, with minor temperature variations that reveal information about the universe's early conditions. These variations match most predictions of the Big Bang theory. However, upon closer examination, astronomers using data from WMAP and Planck satellites noticed something highly unusual. The temperature fluctuations displayed an unexpected alignment along the ecliptic plane, the plane of Earth's orbit around the Sun. This alignment, statistically improbable and counterintuitive, is now recognized as the Axis of Evil. This peculiar alignment has puzzled scientists and led to a variety of explanations. Some have suggested that it could be an artifact caused by the instruments used to measure the CMB, while others believe it could be a result of our position in the universe. This theory suggests that Earth may occupy a special spot in the universe, causing us to observe this alignment from our vantage point. However, this hypothesis has been met with skepticism due to its anthropocentric nature. Another theory posits that the Axis of Evil may be a result of the cosmic bubble collision, where our universe bumps into another parallel universe. This could cause distortions in the CMB, leading to the observed alignment. However, research on this idea is still ongoing and inconclusive. The true origins and implications of the Axis of Evil remain a mystery, but its existence challenges scientists to rethink their understanding of the early universe and its structure. As technology advances and new data is collected, we may one day uncover the secrets behind this enigmatic anomaly and further deepen our understanding of our cosmic origins. Until then, it will continue to intrigue and inspire curiosity among scientists and non-scientists alike. Another theory proposes that the Axis of Evil is evidence of primordial magnetic fields present during the early stages of the universe. These magnetic fields would have influenced particles within the CMB and created this alignment. Why is it called the Axis of Evil? The name, dramatic as it sounds, stems from the trouble it causes from established cosmology. The universe, as per the cosmological principle, is believed to be isotropic and homogeneous on large scales, essentially the same in all directions without any preferred orientation. The Axis of Evil, however, indicates a directional preference, shaking the foundation of this principle. If such an alignment is real and not a fluke, it could mean our understanding of the universe is incomplete, and we might be missing a crucial piece of the cosmic puzzle. This anomaly doesn't just cause philosophical headaches, it has profound implications for physics. If the Axis of Evil persists, it could mean our current models of the universe require significant revisions. It might hint at unknown physics, a more complex cosmic structure, or even interactions beyond our visible universe. Some even suggest it could force us to reconsider theories of inflation or propose entirely new ideas about the universe's early dynamics. Theories abound regarding the causes of the axis of evil. One possibility is that it's nothing more than a statistical fluke, a coincidence that doesn't hold much broader significance. Others suggest local interference could be at play. Dust and other foreground emissions from the Milky Way might have contaminated the data, creating the illusion of alignment. If neither of these explanations suffice, then we're left with more speculative and intriguing possibilities. Some theories propose the axis could be linked to fundamental physics we don't yet understand, or even to multiverse concepts, suggesting our universe may have connections to others. One particularly thought-provoking idea involves the anthropic principle, which posits that the alignment might indicate Earth's position has a unique role in the universe's observed properties. While this idea is controversial and not widely embraced, it adds another layer of mystery and wonder to the conversation. Given all this, what are scientists doing to understand the phenomenon? Satellites like Planck and WMAP have provided detailed observations, confirming the alignment and ruling out simple errors. Yet, the cause remains elusive. Future missions with more precise instruments and advancements in computational modeling might finally offer clarity. Scientists are hopeful that by improving our understanding of the CMB, we can uncover the truth behind this cosmic enigma. Why does solving the axis of evil matter? Beyond its scientific implications, this mystery raises profound philosophical questions. Are the anomalies we see an indication of humanity's unique vantage point in the cosmos? Or are they clues pointing toward new revolutionary physics that could upend what we know about the universe? The axis of evil reminds us that while we've made incredible strides in understanding the cosmos, there are still puzzles that push our imaginations and challenge our theories. Its resolution could be one of cosmology's most significant breakthroughs, opening doors to understanding our universe's origins and structure. Whether an error, a coincidence, or the key to a grander truth, the axis of evil keeps us humble. It shows us that the universe always has more secrets to whisper, waiting for us to listen. Chapter 2: The Dipole Repeller. Imagine standing in a vast, empty desert where an invisible force gently nudges you away from its center. Now, scale that up to the universe, and you'll find something equally mysterious: the dipole repeller. It's not a massive object or a blazing star, but an enormous void shaping the movement of galaxies like an unseen hand guiding a cosmic dance. What could cause such a phenomenon in the boundless depths of space? To understand the dipole repeller, we need to familiarize ourselves with a concept called cosmic flows. Simply put, cosmic flows refer to the large-scale motion of galaxies, driven by the gravitational pull of dense regions and the push of low-density areas in space. When we think about gravity, we often picture it as a force that attracts, pulling objects like stars, planets, and even galaxies toward dense clusters. But what happens when there's a lack of density, a gaping void? This is where the dipole repeller comes into play, a low-density region of space that acts like a counterforce, pushing galaxies away. The dipole repeller sounds like something out of a sci-fi movie, but it's all rooted in scientific discovery. Found in 2017, this cosmic phenomenon was identified by analyzing detailed mapping of galaxy velocities. Scientists relied on the Cosmic Flows 3 survey, an extensive collection of 3D galaxy motion data. By studying these velocity maps, researchers noticed that galaxies were being influenced not just by dense areas, like the gravitational powerhouse known as the Great Attractor, but also by something less obvious, a region with very few galaxies, which they dubbed dipole repeller. Essentially, while the great attractor pulls galaxies toward it, the dipole repeller seems to push galaxies away due to an imbalance in gravitational forces. To detect the dipole repeller, scientists utilize the study of galaxy redshifts. Redshifts are changes in the wavelengths of light emitted by galaxies, which reveal how fast they're moving away from us. Kind of like a fingerprint of cosmic motion, this data enables astronomers to map out the trajectories and speeds of galaxies. Using this information, combined with advanced simulations, researchers could trace the pattern of galaxy movements and infer the dipole repeller's role in reshaping those flows. These simulations showcased how gravitational interactions between high-density and low-density regions dictate the overall layout of the cosmos, much like the choreography of a dance. The dipole repeller itself is fascinating because it isn't a tangible object you can point to. It's a vast void with remarkably low density where galaxies just don't seem to cluster. But don't mistake its subtlety for insignificance. It plays a major role in the cosmic web. The cosmic web describes the sprawling, interconnected framework of the universe, made up of dense clusters and vast empty voids. Imagine a spider's web, where each intersection is a galaxy cluster, and the spaces between strands are like cosmic voids. The dipole repeller represents one of those voids, shaping the movement of those galaxies caught in its influence. The idea of voids shaping cosmic flows isn't entirely new, but the dipole repeller challenges our understanding of gravitational interaction. Traditionally, focus has been placed on how dense regions exert their pull. However, the dipole repeller's existence highlights how low-density voids can exert a kind of passive push. Imagine a seesaw, where a heavy object on one end tilts it downward, but the absence of weight on the other end causes an upward tilt. Similarly, the dipole repeller influences the movement of galaxies, even without the presence of significant mass. One intriguing aspect of studying such voids is their potential connection to dark energy, a mysterious force responsible for the accelerated expansion of the universe. While dense regions with clusters of galaxies are often studied to examine gravitational pulls, low-density voids like the dipole repeller offer a different perspective. They could reveal clues about how dark energy interacts with space on large scales, subtly shaping the cosmic ballet. With ongoing research and advances in technology, we may uncover more secrets about the dipole repeller and its role in the grand dance of the universe. Who knows what other mysterious forces lurk in the vast expanse of space, waiting to be discovered. The dipole repeller also brings to light the importance of new technology and upcoming space surveys. Tools like Euclid and the Roman Space Telescope promise higher resolution data that will allow researchers to map the cosmic web with unprecedented detail. With every technological advancement, we get closer to unveiling more of these elusive voids, which may be scattered across the universe, quietly influencing the celestial dance. While our current models of cosmology provide a strong foundation, discoveries like the dipole repeller underscore the fact that the universe continues to surprise us. It challenges our understanding, urges further exploration, and invites us to see the cosmos not just as a collection of objects, but as a dynamic interplay of forces, both seen and unseen, that shape the fabric of space and time. Without a shadow of a doubt, the dipole repeller is a reminder of the universe's boundless depth and the mysteries waiting to be unraveled. Chapter 3: Galactic Ghost Streams. Imagine delicate trails of light stretching across the dark expanse of the universe, like faint fingerprints left behind by interactions between ancient cosmic giants. These are galactic ghost streams, subtle and mysterious remnants of galactic collisions and mergers that serve as historical records of the universe's dynamic evolution. These streams, composed of stars and gas, are the products of gravitational encounters, a cosmic tug-of-war between galaxies that pull material into elongated trails. Despite spanning vast distances, they are so faint and ephemeral that they challenge even the most advanced methods of detection, fading over time as their stars disperse and lose cohesion due to the constant motion within the galaxy. Galactic ghost streams form when galaxies, drawn together by their immense gravitational forces, interact with one another. These encounters often involve processes such as tidal forces, the cosmic equivalent of stretching and pulling, that strip stars and gas away from galaxies, leaving behind these spectacular yet faint trails. Sometimes, these streams emerge from smaller dwarf galaxies falling prey to larger ones, a phenomenon known as galactic cannibalism. A striking example of this is the Sagittarius stream, located within our own Milky Way galaxy. This stream was created when a smaller galaxy, the Sagittarius dwarf galaxy, began its slow merger into the Milky Way, leaving behind a trail of stars that arcs across the sky like a ghostly whisper of the celestial past. Yet uncovering these ghostly remnants is far from simple. Their low surface brightness, the faint light they emit, makes them almost invisible against the cosmic backdrop. Astronomers rely on a combination of advanced tools and techniques to locate these elusive structures. Wide-field optical surveys and infrared imagery are instrumental in detecting the faint glow of the dispersed stars. Long exposure imaging further enhances visibility, allowing astronomers to reveal details that would otherwise remain hidden. Even with these technologies, the task is daunting, as these delicate streams blend into the star-studded tapestry of the universe. The challenge doesn't stop at detection. Galactic ghost streams are as perplexing as they are beautiful. They often defy our current models of galaxy interactions, their structures and distributions revealing patterns that don't align with established theories. Their fleeting nature adds to the enigma. They are rare finds, and each discovery potentially rewrites a chapter of the universe's story. These streams offer glimpses into the hidden history of galaxies, exposing past collisions and mergers that might have otherwise left no trace. By studying them, astronomers can better understand the processes that shape galaxies and contribute to the evolution of the universe. As our understanding of these ghostly structures continues to evolve, so does our appreciation for their significance. They are not just beautiful cosmic apparitions, but also valuable tools in unraveling the mysteries of the cosmos. With improved technology and innovative approaches, we may one day unlock more secrets hidden within these ethereal galactic remnants, shedding light on the ever-evolving universe that surrounds us. So, next time you gaze up at a starry sky, remember that beyond what meets the eye is an intricate network of galactic ghost streams waiting to be discovered and explored. The discovery and study of galactic ghost streams also highlights humanity's ingenuity and relentless pursuit of understanding the cosmos. By piecing together evidence from these faint trails, astronomers can unlock the secrets of how galaxies grow and interact over billions of years. Each stream represents a fragment of a larger cosmic puzzle, giving us insight into the forces at play in shaping the universe's grand design. These studies also push the boundaries of technology, prompting the development of new instruments and methods capable of detecting even fainter and more distant streams. Furthermore, galactic ghost streams teach us about the cyclical nature of the universe. From the remnants of these collisions can come new patterns of star formation, as gas compressed during these interactions fuels the birth of new stars. Over eons, these processes weave a rich and complex tapestry that links the past, present, and future of galaxies. Through these faint vestiges, we are reminded that the universe is not static, but a vibrant, dynamic entity, constantly evolving and reshaping itself in ways that are both chaotic and awe-inspiring. The study of ghost streams also brings a humbling perspective to humanity's place in the cosmos. These ethereal remnants are a testament to the longevity and scale of cosmic processes, a reminder that long before Earth existed, galaxies were already playing out their intricate dance across the universe. And even now, alongside these distant interactions, our galaxy is engaging in gravitational encounters of its own, reshaping itself in ways imperceptible to us but vital to the broader narrative of the cosmos. Each discovery not only deepens our understanding, but ignites our curiosity to uncover what lies beyond. To understand the full story behind these structures, astronomers employ sophisticated computational models and simulations, creating digital replicas of galactic interactions to reconstruct the formation of these streams. By observing how stars and gas move within these models, scientists can piece together how the streams came to be and what they might tell us about the host galaxies' histories. Future missions, like the Vera C. Rubin Observatory, promise to be game changers, with their powerful, next-generation telescopes set to unveil many more ghost streams. This will not only expand our catalog of discoveries, but also refine our understanding of the cosmos, helping to solve some of the mysteries that these eternal trails still hold. Galactic ghost streams, though faint and fleeting, offer an extraordinary portal into the grand narrative of the universe. They are the silent witnesses of celestial collisions, their presence whispering tales of tumult, transformation, and time itself. Their study continues to push the boundaries of what we know about galaxies and their interactions, making them one of the most mesmerizing subjects in modern astronomy. Chapter 4. Polarization of Quasars. Quasars, among the brightest and most distant objects in the universe, captivate astronomers and astrophysics enthusiasts alike. These incredibly luminous entities are powered by supermassive black holes at the centers of galaxies, which consume surrounding material at astonishing rates. During this process, they emit vast amounts of energy, making them visible from billions of light years away. However, one of the most intriguing aspects of quasars is not just their brightness, but the way their light becomes polarized. Polarization is a fascinating property of light, where the oscillations of light waves align in specific directions. It offers astronomers a window into the environments around quasars, adding an extra layer of mystery to these cosmic powerhouses. To understand polarization, it's helpful to think of light as a wave that vibrates in different directions. Normally, these waves are unorganized, oscillating in all possible directions perpendicular to their path of travel. However, when light becomes polarized, its waves align in one dominant direction. This alignment can occur due to specific interactions, such as scattering by particles, reflections off surfaces, or the presence of magnetic fields. When it comes to quasars, the polarization of their light reveals valuable insights about the extreme and dynamic environments they exist within. Light from these objects interacts with their surroundings, including particles and intense magnetic fields, before it reaches us. What makes polarization in quasars particularly unique is how pronounced and unusual it can be compared to most other astronomical objects. This reflects the extreme conditions in the vicinity of quasars. Near these supermassive black holes, the environment is chaotic, with swirling disks of matter, intense radiation, and powerful magnetic fields. These forces and interactions shape the behavior of light, creating polarization patterns that are far beyond what we see in quieter celestial phenomena. The study of polarized light from quasars allows scientists to better understand the structure and dynamics of these environments, shedding light on the invisible magnetic forces and the scattering mechanisms at play. Detecting this polarization is no simple feat. astronomers rely on highly specialized tools like polarimeters to measure the degree and angle of polarization in light from quasars. These instruments are capable of detecting even incredibly faint signals, offering detailed information about where and how the alignment of light waves occurs. By analyzing these measurements, astronomers can determine the orientation of magnetic fields and the nature of scattering processes happening near quasars. This combination of technology and analysis helps paint a clear picture of one of the most energetic and enigmatic processes in the universe. One of the mysteries surrounding quasar polarization is the discovery of large-scale patterns in how these light waves align. Astronomers have found that the polarization angles of light from quasars separated by billions of light years seem to exhibit strange alignments. Such coherence across such vast distances is puzzling, as these quasars are far too distant from one another to be directly interacting. The statistically improbable nature of this alignment raises questions that challenge conventional astrophysical expectations. It also hints at potential connections on a cosmic scale that scientists are still working to understand. Although these alignments remain an enigma, there are some plausible explanations rooted in current astrophysical understanding. One possibility is that light from these quasars interacts with magnetic fields in the intergalactic medium, which fills the vast space between galaxies. These magnetic fields may create patterns or influences that align the polarization of light as it travels through these regions. Another idea is that large-scale structures of the universe, known as cosmic filaments, may contribute to this phenomenon. These filaments form a web-like network that spans the cosmos and could affect the light that passes through them. Alternatively, the early conditions of the universe itself may have left imprints on light that has traveled huge distances over billions of years. Despite these theories, observing and interpreting quasar polarization is fraught with challenges. The signals themselves are incredibly faint, requiring astronomers to use instruments of exceptional sensitivity. Additionally, as light traverses the vast expanses of the universe to reach Earth, it encounters constant obstacles. Dust clouds, intergalactic particles, and various gravitational effects can distort the original light, making it even more difficult to isolate and understand its polarization characteristics. These hurdles make the study of quasar polarization both a technical and scientific challenge, requiring meticulous observation and analysis. Quasar polarization may seem like just one part of their complex nature, but it opens up a profound window into some of the most extreme environments and forces in the universe. It provides not only a glimpse into the immediate surroundings of these distant objects, but also clues about the cosmic structures and conditions they interact with over enormous scales. As scientists continue to study polarized light from quasars, they inch closer to unraveling the mysteries of these dazzling and dynamic beacons of the cosmos. Chapter 5: The Kuiper Belt Mystery. The Kuiper Belt is a sprawling region of icy objects that stretches beyond the orbit of Neptune. It's often referred to as the edge of the solar system, home to some of the most fascinating remnants of the early solar system, such as comets, icy debris, and even dwarf planets like Pluto. For many years, astronomers believed that the Kuiper Belt extended smoothly into the outer reaches of the solar system, gradually thinning out as the distance from the Sun increased. However, when scientists began mapping this distant region, they discovered something unexpected. Objects within the Kuiper Belt suddenly drop off in density at a distance of roughly 50 astronomical units, or AU, from the Sun. This abrupt decline is now known as the Kuiper Cliff. The Kuiper Cliff is not just a minor anomaly. It marks a significant and largely mysterious feature of our solar system. To put it in perspective, instead of the anticipated gradual fading of Kuiper Belt objects, or KBOs, as one moves farther from the Sun, there is an unanticipated, sharp cutoff. At around 50 AU, the distribution of these icy objects nearly vanishes, leaving a puzzling void in a region where we expected to find more. This phenomenon was discovered through detailed telescopic surveys aimed at understanding the distribution and density of KBOs. Observations from tools like the Hubble Space Telescope, as well as powerful ground-based observatories, allowed scientists to track KBOs and map them with increasing accuracy. These observations revealed the unexpected void, prompting debates and discussions about what might explain the Kuiper cliff. What makes the Kuiper cliff so intriguing is the dramatic scarcity of objects beyond the 50 AU threshold, something not observed in other regions of the solar system. Beyond this point, KBOs are almost entirely absent. This sudden drop-off is unlike the patterns we see closer to the Sun and hints at a range of questions about the formation and evolution of the outer solar system. It's a feature that stands out in its mystery and uniqueness, compelling astronomers to investigate further. Several theories have been proposed to explain the Kuiper cliff. One leading hypothesis is the gravitational influence of an unknown massive object, potentially the elusive Planet 9. This hypothetical planet, which has yet to be directly observed, could be exerting its gravitational pull on KBOs, effectively clearing them out beyond the cliff. Such an object would need to be several times the mass of Earth and located far beyond the Kuiper belt. Another possibility is that early solar system processes may have cleared out this region of debris. During the chaotic early phases of the Sun's formation, gravitational interactions between young planets and smaller icy bodies could have ejected these objects from the solar system altogether, leaving the area beyond the Kuiper cliff largely barren. A third theory is related to the natural limits of planetary formation. It's possible that during the solar system's formation, the distribution of materials was such that icy bodies couldn't form or coalesce beyond a certain distance from the Sun. This would result in a natural cutoff, creating the impression of a cliff in the density of objects. Further research and observations are needed to determine which, if any, of these theories may hold the key to unlocking the mystery of the Kuiper cliff. In addition to its potential implications for our understanding of solar system formation, the Kuiper cliff also poses exciting opportunities for future exploration. The New Horizons spacecraft, which provided us with unprecedented images and data about Pluto and its moons in 2015, is now on a trajectory towards another KBO called Arrokoth. This distant world was chosen specifically because it lies beyond the Kuiper cliff, offering scientists a rare opportunity to study an object in this mysterious region of the solar system. Studying the Kuiper cliff has proven to be an extraordinary challenge. Observing objects this far away is inherently difficult due to their small size and faintness. With KBOs reflecting only a tiny fraction of sunlight, telescopes face significant limitations in detecting them, especially at such extreme distances from Earth. Additionally, observational biases, such as where telescopes are able to point and how wide their observational fields are, restrain our understanding of the true distribution of KBOs. These constraints make it difficult to confirm whether the Kuiper cliff is as abrupt as it seems, or if improvements in technology might reveal more distant populations of objects. Despite these challenges, studying the Kuiper cliff is critically important for understanding the broader history and structure of our solar system. Its existence offers a unique window into the early processes that shaped our solar system, providing clues about how planets and smaller icy bodies formed, migrated, and interacted over billions of years. Furthermore, the Kuiper cliff challenges and refines current models of the solar system, forcing scientists to rethink their understanding of its outermost regions. The sharp drop-off in KBOs poses fundamental questions about planetary formation, gravitational dynamics, and the distribution of materials during the solar system's chaotic infancy. From a scientific viewpoint, the Kuiper cliff is not just a puzzling feature, it's an opportunity, an open invitation to investigate the unknown. Whether its origins lie in the pull of a hidden planet, the violent history of the early solar system, or the natural boundaries of planetary formation, the Kuiper cliff continues to intrigue and captivate astronomers. Unraveling its mysteries will undoubtedly reshape how we view the outer reaches of the Sun's domain, and perhaps even shed light on other planetary systems beyond our own. The Kuiper cliff's sharp, empty silence challenges us to explore further, to look deeper, and to question the boundaries of what we know about our cosmic neighborhood. Chapter 6: Magnetars' Extreme Behavior. Magnetars are celestial powerhouses that redefine the extremes of physics. Imagine a star with a magnetic field so intense that it could erase the data on a credit card from halfway across the moon. That's the world of magnetars, a type of neutron star considered among the rarest and most mysterious objects in the universe. With only about 30 confirmed magnetars, these fascinating remnants of massive stars have captivated astronomers and space enthusiasts alike. When a star far larger than our Sun exhausts its nuclear fuel, it may explode in a supernova, leaving behind a dense core known as a neutron star. Magnetars are a specialized subset of neutron stars, but what sets them apart is their mind-bendingly strong magnetic fields. To put this into perspective, Earth's magnetic field is about 0.5 Gauss, while a fridge magnet is around 100 Gauss. Magnetars, on the other hand, boast magnetic fields that reach up to an astonishing 10 to the 15th power Gauss, making them the most magnetic objects in the known universe. This extreme magnetism shapes not only their behavior, but also the surrounding space, stretching and warping magnetic field lines in ways scientists are still striving to understand. Magnetars are rare and volatile, offering a glimpse into some of the universe's most extreme phenomena. Their overpowering magnetic fields exert immense stress on the star's crust, creating what scientists call starquakes. Similar to tectonic earthquakes on Earth, but on a vastly greater scale, these starquakes occur when the crust of the magnetar shifts and fractures under the strain of its magnetic field. The energy released during these events rivals our Sun's total energy output over 100,000 years, packed into just a few seconds. The result? Dazzling bursts of X-rays and gamma rays that can be detected from across the cosmos. These outbursts, also known as gamma-ray flares, highlight the staggering power magnetars can release in a heartbeat. One defining characteristic of magnetars is their rotational behavior. When they first form, they spin at blinding speeds, completing a full rotation in less than a second. Over time, however, their immense magnetic fields act as a brake, gradually slowing their rotation. Today, most magnetars spin once every few seconds, a snail's pace in cosmic terms, yet still astonishing when you consider the enormity of these objects. This gradual slowing, called spin down, is another feature scientists study to unlock the secrets of these magnetic titans. Perhaps one of the most intriguing associations magnetars have is with fast radio bursts, or FRBs. These mysterious, millisecond-long flashes of radio waves have puzzled astronomers since their discovery. Some FRBs are believed to originate from magnetars, owing to the immense bursts of energy they generate. Yet, despite years of research, the exact mechanism behind FRBs remains a cosmic enigma. Are they caused by magnetic field reconnection events, starquakes, or something entirely unexpected? The mystery keeps magnetars at the forefront of astrophysical research. Studying magnetars requires specialized tools capable of peering into the high-energy extremes of the universe. Space-based telescopes like NASA's Chandra X-ray Observatory and Swift Observatory are instrumental in capturing the X-ray and gamma-ray emissions from magnetar flares. Meanwhile, radio telescopes scattered across the globe keep a vigilant watch for the elusive FRBs that might deepen our understanding of these objects. However, observing magnetars is no easy feat. Their rarity and unpredictable outbursts make capturing and studying them a challenge, pushing the limits of modern astrophysical technology and techniques. The environments around magnetars are so extreme that they stretch the boundaries of what is possible within our current understanding of physics. They allow scientists to study matter under nearly incomprehensible conditions, such as unimaginable densities and magnetic intensities. These cosmic laboratories serve as bridges connecting the physics of neutron stars, black holes, and other exotic objects. Despite their ferocity and rarity, magnetars remain a crucial piece of the puzzle in understanding the life cycles of stars and the behavior of matter under extreme conditions. Their study not only deepens our knowledge of stellar evolution, but also provides insights into fundamental physics, such as quantum mechanics and general relativity. Magnetar research has implications that stretch far beyond astronomy, influencing fields like materials science and nuclear physics as scientists explore how atomic structures withstand such colossal forces. Interestingly, magnetars also play a role in explaining certain cosmic mysteries. For example, their powerful magnetic fields and intense energy emissions are viewed as potential explanations for soft gamma repeaters, or SGRs, celestial phenomena involving repeated bursts of gamma rays and X-rays. Observations of these events often align with the locations of known magnetars, reinforcing the connection between these exotic objects and the powerful high-energy emissions detected throughout the universe. The study of magnetars is far from complete. With advancements in observational technology and theoretical modeling, scientists are slowly unraveling their secrets. Future missions, such as the European Space Agency's Athena X-ray Observatory, promise to deliver even more detailed observations of magnetar behavior, particularly their dynamic flares and rotational changes. Additionally, the ongoing hunt for more fast radio bursts will likely solidify the link between these enigmatic signals and magnetars, helping to solve one of astronomy's most persistent mysteries. Magnetars continue to remind us of the universe's boundless capacity to amaze and challenge our understanding. These celestial powerhouses act as cosmic laboratories for testing the limits of physical laws, offering glimpses into regions of space that remain largely uncharted. Every discovery tied to magnetars not only enhances our knowledge of the cosmos, but also inspires future generations of scientists to probe deeper into the unknown, ensuring that the study of these otherworldly objects remains a vibrant and evolving field of exploration. While much has already been discovered about magnetars, their full implications for the universe remain tantalizingly out of reach. For example, recent theories suggest that magnetars might play a pivotal role in the creation of some of the heaviest elements in the cosmos, such as gold and platinum. These elements are typically formed during catastrophic cosmic events, like neutron star mergers, but the immense energy and magnetic forces associated with magnetar outbursts may also contribute to their synthesis. If confirmed, this would significantly expand our understanding of how the building blocks of planets and even life itself are forged. Furthermore, magnetars may offer insights into the mysterious dark matter that pervades the universe. Some researchers speculate that interactions between magnetar magnetic fields and hypothetical particles like axions might produce detectable signals, offering a new way to probe this elusive component of the cosmos. Such discoveries could bridge the gap between astrophysics and particle physics, highlighting the interdisciplinary nature of modern space science. The role of magnetars in galactic ecosystems is another exciting area for further exploration. Their powerful outbursts can affect surrounding interstellar environments, triggering the formation of new stars or dispersing nearby gas clouds. This means that magnetars, despite being rare and short-lived, might influence the evolution of galaxies on immense scales. Understanding their influence could reshape our perception of the dynamic processes that govern the evolution of the universe. Ultimately, the study of magnetars exemplifies humanity's quest for knowledge. These enigmatic stars challenge the limits of human ingenuity and inspire collaboration across scientific disciplines. With every new observation, magnetars continue to push the boundaries of what we know, offering profound insights into the workings of the cosmos and our place within it. Whether as agents of cosmic creation or as keys to unraveling fundamental mysteries, magnetars will undoubtedly remain a focal point of astrophysical research for decades to come. Magnetars remain one of the universe's most fascinating and mysterious ingredients, offering profound insights into the forces that govern our cosmos. Each observation, every starquake, and every gamma ray burst adds another piece to their awe-inspiring puzzle. Magnetars remind us of just how much we still have to learn about the universe and how far we are willing to go to uncover its secrets. Chapter 7: The Uranus Core. Uranus stands as one of the solar system's greatest enigma, a giant world veiled in mystery. Despite being the third largest planet in our cosmic neighborhood, it is among the least understood. This turquoise gem, over 1.8 billion miles away from the Sun, has captivated astronomers for centuries, not only for its peculiar tilt on its axis, but also for the secrets buried deep within its core, a region no spacecraft or instrument has directly explored. What exactly lies at the heart of Uranus, and why does it behave so differently from its fellow ice giants? This captivating mystery begins with the planet's structure. Surrounding Uranus is an atmosphere primarily composed of hydrogen and helium, with a touch of methane, which gives the planet its iconic blue-green hue. Beneath this gaseous layer lies an extensive mantle of water, ammonia, and methane, existing in a state neither fully liquid nor gas, what scientists call a supercritical fluid. This strange state is the result of the planet's immense pressure and frigid temperatures. Deeper still, at its heart lies the core, a dense region made of rock and metal, shrouded in even more mystery than Uranus's outer layers. What sets Uranus apart from other giant planets like Jupiter and Neptune is not just its composition, it's the planet's internal heat, or rather, the lack of it. Unlike its neighbor Neptune, which emits more heat than it receives from the Sun, Uranus barely radiates any internal heat. This anomaly has led scientists to question why Uranus is so cold and inert compared to similar-sized planets. One prominent theory suggests a cataclysmic event in its early history. Imagine an Earth-sized object colliding with Uranus billions of years ago with such force that it knocked the planet onto its side. This massive impact could have disrupted the planetary core, potentially stalling internal heat flow and leaving Uranus with its uniquely low thermal activity. But what lies within the core of Uranus that makes it so enigmatic? Current models suggest its core is dense, made predominantly of rock and metal, but the specifics remain unknown. Under the immense pressure and temperature at the planet's center, otherworldly materials like superionic ice could exist. This exotic form of water is neither solid nor liquid. It's a structure where oxygen atoms form a crystalline lattice, allowing hydrogen ions to flow freely. Such conditions are unlike anything we experience on Earth, offering a glimpse into the extreme physics shaping the universe's icy realms. The pressure at the core of Uranus is mind-boggling, measuring millions of times greater than Earth's atmospheric pressure. Temperatures, while reaching thousands of degrees, are unexpectedly low for a planet of its size. This combination of high pressure and relatively cooler temperatures challenges scientists, leading to ongoing debates about the formation and evolution of Uranus. Could its internal structure hold clues to understanding other ice giants or even exoplanets in distant solar systems? Despite its mysteries, our knowledge of Uranus largely stems from a fleeting encounter. Voyager 2, the only spacecraft to visit the planet, flew by in 1986, capturing brief data that remains invaluable. Yet, its findings only scratched the surface, or more aptly, skimmed the atmosphere. Uranus's thick layers, remote location, and lack of subsequent missions have left its core an unsolved puzzle. However, astronomers are hopeful that future missions and advanced telescopes will one day provide breakthroughs, uncovering the secrets of this icy world. As our understanding of Uranus continues to evolve, so too will the stories and theories surrounding this enigmatic planet. Who knows what exciting discoveries lie ahead? Perhaps one day we will finally know what truly lies within Uranus. So let's keep exploring and unraveling the mysteries of this distant world. There is still so much to learn and discover about Uranus and its place in our solar system. From studying its unique tilt, rings, and moons to delving deep into its core, there is no doubt that new revelations await us in the future. Additionally, with advancements in technology and space exploration, we may even be able to send a mission directly to Uranus's core one day. Imagine the wealth of information and data we will gather from this once-in-a-lifetime opportunity. It could potentially unlock the secrets of not only Uranus, but also provide insights into the formation and evolution of other icy worlds in our universe. But for now, let us continue to marvel at the mysterious beauty of Uranus and appreciate its importance in our solar system. Who knows what new discoveries await us as we continue to push the boundaries of science and exploration. The possibilities are endless when it comes to understanding this distant giant, so let's never stop seeking answers about Uranus. One thing is for sure, there is still so much more to be uncovered about this captivating enigma. The core of Uranus, hidden beneath its ethereal blue haze, remains one of the solar system's most tantalizing mysteries. From its peculiar tilt and suppressed heat flow to the potential existence of exotic materials, every detail about its center offers a new layer of intrigue. Uranus invites us to push the boundaries of our understanding, challenging us to unlock the secrets that lie beneath its frozen skies. For now, we can only ponder the invisible forces and unimaginable conditions shaping its enigmatic heart, patiently awaiting the day when science finally pierces through its mysteries. What do you think lies at the core of Uranus? Share your thoughts in the comments below. There's still so much to discover. Chapter 8: The Cosmic Lithium Problem. The universe never ceases to amaze and puzzle us. Among its many unsolved mysteries, the cosmic lithium problem ranks as one of the most perplexing. Lithium, a fundamental chemical element produced in the earliest moments of the universe, is at the center of this enigma. While hydrogen and helium, the other light elements created during the Big Bang, perfectly align with theoretical predictions, lithium does not. What we observe doesn't match what we expect, and astrophysicists have been grappling with this disparity for decades. Lithium, as you might know, is an essential element with countless applications here on Earth, from batteries to medicine. But in the cosmic context, its significance lies in its origin. Shortly after the Big Bang, the universe was an incredibly hot, dense state of matter and energy. It was during this brief window, just the first few minutes, that the process of Big Bang nucleosynthesis occurred. This was when the building blocks of matter as we know it were first formed, including light nuclei like hydrogen, helium, and lithium. These processes established the initial abundance of the universe's elements, providing the foundation for stars, galaxies, and eventually life itself. Big Bang nucleosynthesis models are highly effective at predicting the primordial abundances of hydrogen and helium. These predictions have been corroborated by observations, instilling confidence in our understanding of early universe physics. However, when it comes to lithium, there's a glaring mismatch. Specifically, astrophysical models significantly overestimate the amount of lithium-7, the most stable isotope of lithium, compared to what we observe in the ancient stars, often referred to as metal-poor stars. These stars, which have existed for billions of years, are thought to preserve a snapshot of the primordial universe's chemical composition, making the lithium discrepancy impossible to ignore. The observed lithium discrepancies are not minor, they are striking. Models predict 3 times more lithium-7 than what we find when observing these ancient stars. This mismatch raises questions about the physics of the early universe and challenges some of the foundational principles of cosmology. What's even more intriguing is that the problem doesn't apply to hydrogen or helium. For those elements, the theories and observations are in beautiful harmony, but lithium stubbornly stands apart, as if the universe is keeping part of its creation story hidden from us. Over the years, numerous potential explanations for this discrepancy have been proposed. The first possibility points to the stars themselves. It is believed that lithium in ancient stars might not be as stable as we thought. Certain stellar processes could gradually destroy lithium, causing its abundance to drop over time. This would mean that the observed lithium levels in stars are not representative of the primordial quantities. However, even if this exploration accounts for some of the discrepancy, it doesn't tell the entire story. The gap between theory and observation is simply too broad. Another possibility lies in the production errors during Big Bang nucleosynthesis itself. This would suggest that our theoretical understanding of early universe physics, widely regarded as robust, is incomplete. Could there be unknown aspects of nuclear reactions that occur under extreme temperatures and densities? Or perhaps the involvement of exotic particles reshape the production of lithium-7 in ways we are yet to fully comprehend. While it sounds speculative, such possibilities are actively explored in theoretical physics. Then there's the hypothesis that lithium could be hiding in plain sight. Some researchers propose that lithium may exist in inaccessible regions of stars, or that it is trapped in a way that prevents it from being directly observed. Similarly, it could be bound to certain chemical processes occurring in stellar atmospheres, making it appear as though less lithium exists than is actually present. These ideas seek to explain why what we see through our telescopes doesn't reflect the models we rely on. Complicating matters further, lithium consists of 2 isotopes, lithium-6 and lithium-7. While lithium-7 is far more common and central to the cosmic lithium problem, the occasional detection of lithium-6 in higher than expected amounts adds an additional layer of complexity. This rare isotope complicates our understanding of lithium formation and distribution. The presence of lithium-6 where we least expect it deepens the mystery. The observational challenges only add to the difficulty of solving this problem. Measuring lithium abundance in ancient stars is no small feat. These measurements rely heavily on precise spectroscopic analysis, which can only provide indirect evidence of an element's presence and quantity. Factors like temperature, stellar atmospheres, and even minor misinterpretations in data can skew results, making accurate measurements elusive. Perhaps one of the most striking aspects of this puzzle is its uniqueness. The predictions for hydrogen and helium, the other elements formed during Big Bang nucleosynthesis, are remarkably accurate when compared with observations, but lithium continues to defy explanation. This discrepancy serves as an outlier, a challenge to the otherwise harmonious picture of early universe processes. Scientists aren't without tools or progress, though. Ground-based telescopes and space missions like Planck have refined our understanding of primordial element abundances and continue to provide invaluable data. Theoretical models and simulations have become increasingly sophisticated, providing deeper insights into particle interactions and extreme cosmic conditions. Researchers are also studying stellar and galactic contributions to lithium abundance. It's worth noting that while some lithium is created during a star's life cycle, other cosmic processes, like spallation caused by cosmic rays, can also produce negligible amounts of lithium. However, these processes fall short of explaining the missing primordial lithium. Ultimately, the gap between observation and theory remains an unsolved mystery, standing as one of the most significant anomalies in contemporary astrophysics. Every proposed explanation addresses part of the problem, yet leaves other questions unanswered. The cosmic lithium problem is a reminder of both the power and the limitations of human understanding. It underscores how much we've learned about the universe, while humbling us with the realization of how much more there is to uncover. The cosmic lithium problem is, at its heart, a fascinating enigma, an enduring puzzle that continues to captivate astronomers, physicists, and space enthusiasts alike. Scientists around the world are driven by the challenge of solving this problem, knowing that doing so will bring us one step closer to understanding the origins of our universe. The lithium may be missing, but the search for answers burns brighter than ever. Chapter 9: Intergalactic Radio Signals. Intergalactic radio signals are a fascinating window into the unknown, giving us a glimpse of phenomena taking place far beyond our own Milky Way galaxy. These mysterious signals are radio waves that originate in galaxies light years away and differ significantly from the well-known fast radio bursts, or FRBs. While FRBs are short, intense emissions lasting only milliseconds, intergalactic radio signals tend to be more continuous, less pronounced, and of varying durations. Their consistent detection challenges our understanding of the cosmos and invites us to explore their intriguing origins. The sources of intergalactic radio signals are as diverse as the galaxies they come from. Pulsars, which are rapidly rotating neutron stars, are thought to be responsible for some of these signals due to their ability to emit focused radio waves in periodic bursts. Active galactic nuclei, powered by supermassive black holes at the center of distant galaxies, are another likely source. These titanic entities can emit radio waves as they consume surrounding matter, or, on an even grander scale, some signals may be remnants of ancient cosmic events, such as collisions between galaxies or megascale particle interactions that occurred billions of years ago. But despite our growing knowledge, many intergalactic radio signals remain unexplained, underscoring the mystery of their true nature. Detection of these signals is no small feat. Specialized radio telescopes like the Very Large Array, or VLA, LOFAR, and ASCAP are central to the process. These instruments, armed with advanced technology, search vast regions of the sky to capture faint radio waves traveling unimaginable distances. Interferometry, a technique used to combine signals from multiple telescopes, plays a crucial role in pinpointing the locations of these emissions with extraordinary precision. This allows scientists to map where the signals originate within distant galaxies, offering valuable contextual information about the environment in which they arise. The properties of intergalactic radio signals add yet another layer of complexity to their study. These signals vary widely in strength, frequency, and duration, with some displaying continuous patterns while others are sporadic or even periodic. They also span different radio frequency bands, meaning they can cover a wide range of wavelengths. Certain signals remain especially perplexing, originating from what appears to be intergalactic voids, vast stretches of space between galaxies that seem unlikely to host any conventional astrophysical sources. These properties not only make the signals difficult to classify, but also ignite debates among astrophysicists about their origins. Despite advances in detection technology and methodology, the study of intergalactic radio signals is riddled with challenges. The immense distances involved make it incredibly hard to determine precise origins, a dilemma further complicated by cosmic noise. This background noise, caused by natural radio emissions from stars, galactic activity, and even Earth-based interference, often obscures weaker signals. Additionally, because these signals are rare and fleeting, researchers struggle with limited observational data, making it difficult to draw definitive conclusions. Various scientific theories attempt to explain the origin of intergalactic radio signals, yet no single hypothesis accounts for all observations. For example, synchrotron radiation is often discussed as a potential source. This process involves high-energy particles spiraling around magnetic fields, releasing radio waves in the process. Some researchers suggest that interactions between dark matter and baryonic matter could also produce such emissions, though these ideas remain speculative. The lack of a unifying theory underscores just how much we have yet to understand about these signals. It is also important to distinguish intergalactic radio signals from fast radio bursts, as the two are fundamentally different phenomena. FRBs are remarkably short and intense, typically associated with energetic cosmic events like magnetar activity or supernova remnants. Conversely, intergalactic radio signals are more continuous or longer-lasting and lack consistent associations with specific astrophysical events. This makes their study more challenging, as they do not neatly fit into the existing frameworks scientists have established for interpreting cosmic radio waves. The importance of studying intergalactic radio signals cannot be overstated. These signals serve as unique probes into intergalactic space and the physical processes that govern it. By analyzing them, we gain deep insights into the composition, structure, and evolutionary history of the universe, far beyond our local galactic neighborhood. Every piece of the puzzle brings us closer to understanding the cosmic tapestry of which we are but a tiny part. Chapter 10. Interdust Clouds. Interdust clouds are some of the most enigmatic and fascinating phenomena in our universe. These diffuse accumulations of microscopic particles, composed of silicates, carbon, and ice, are scattered across the expanses of interstellar space. Though they lack the density of molecular clouds, their significance to the galactic ecosystem is undeniable. From serving as material reservoirs for star formation to their mysterious behaviors and origins, interdust clouds hold secrets that challenge our understanding of the cosmos. At their core, interdust clouds are remnants of cosmic processes. The dust grains that make up these ancient clouds largely originate from ancient stars, supernova explosions, and other cataclysmic events in the life cycles of celestial bodies. These tiny particles, spanning mere microns, might sound significant on their own, but they aggregate to form clouds that can stretch across light years. Despite their vastness, interdust clouds remain diffuse, which separates them from the denser molecular clouds where stars actively form. One of the defining characteristics of interdust clouds is their interaction with light. These clouds absorb and scatter starlight, producing effects such as interstellar extinction and reddening. Interstellar extinction, for instance, leads to the dimming of starlight as it passes through these clouds, making distant stars appear fainter to observers on Earth. Similarly, reddening occurs because the clouds scatter blue light more efficiently than red, giving stars viewed through them a reddish hue. While these effects contribute to the beauty of the night sky, they pose significant challenges for astronomers trying to study distant celestial objects and their properties. However, it's not just their light-dimming properties that intrigue scientists. Some interdust clouds are located in regions of space where there is no active star formation, raising the question of how and why they formed in these locations. Without ongoing stellar activity to replenish the materials that compose the clouds, their presence in such areas defies conventional understanding. Are they relics of past events, or are there processes at play that have yet to be discovered? The answers remain elusive. Studying these clouds is no small feat. Interdust clouds emit very little visible light, making them challenging to detect through traditional optical telescopes. Instead, researchers rely on infrared and radio wavelengths to observe them. Instruments like the James Webb Space Telescope, JWST, and the Atacama Large Millimeter Submillimeter Array, ALMA, are indispensable for detecting the faint heat emissions of those dust grains and understanding their distribution and properties. Spectroscopy, another vital tool in this endeavor, allows scientists to analyze the cloud's chemical makeup by studying how light interacts with the various elements and compounds within them. One of the more intriguing roles of interdust clouds is their potential contribution to star formation. While molecular clouds are the recognized birthplaces of stars, interdust clouds may act as precursors to these denser regions. By serving as enormous reservoirs of raw materials, they provide the building blocks needed for molecular clouds to form, and, subsequently, for stars to be born. This possibility reinforces their integral role in the ongoing cycles of matter and energy that shape galaxies. Despite the progress made in understanding interdust clouds, they continue to mystify astronomers. Some of these clouds display unexpected chemical compositions that do not align with current models of dust production. Others exhibit anomalous scattering behaviors that defy existing theories. These mysteries indicate that there's still much we don't know about these cosmic structures and their interactions within the galactic environment. Interdust clouds are not isolated entities. They are dynamic components of the galaxy. Their motions and distributions are influenced by magnetic fields, stellar winds, gravity, and other forces that weave together the fabric of interstellar space. By studying their interactions with these forces, astronomers can glean valuable insights into the broader dynamics of galaxies and the behavior of interstellar matter. However, their vast presence comes with a downside for cosmic observations. Interdust clouds often obscure celestial bodies, making it difficult for astronomers to study stars, planets, and galaxies that lie behind them. They complicate measurements of cosmic distances as well. For example, astronomers use the brightness of certain supernovae as standard candles to measure vast intergalactic distances. The presence of interdust clouds can distort these measurements, introducing uncertainties into critical cosmological data. Understanding the nuances of these clouds is essential for accurate interpretations in the field of space studies. Thankfully, advanced tools and techniques are helping scientists overcome these challenges. Infrared capabilities have proven invaluable for peering through the obscuration of interdust clouds, while spectroscopy and other methodologies continue to unveil details about their composition and behavior. Instruments like the JWST promise to provide even greater resolution and insight into these diffuse clouds, pushing the boundaries of our knowledge. Interdust clouds are essential yet enigmatic players in the galactic ecosystem. They serve as reservoirs of material for future star formation, interact dynamically with various galactic forces, and leave a profound impact on cosmic observations. At the same time, their origins, compositions, and behaviors hold mysteries that continue to challenge established models in astronomy. By studying interdust clouds, we not only learn about the interstellar medium, but also gain deeper insights into the dynamics of our universe. These diffuse yet impactful accumulations of dust invite us to explore questions about where they come from, how they evolve, and what roles they play in shaping the cosmos. Though they're faint and elusive, interdust clouds shine brightly as a frontier of astronomical discovery. As we journey through the vast expanse of the universe, exploring the mysteries and anomalies that reside within, we are reminded of the sheer wonder and beauty that exists beyond our own planet. From enigmatic black holes to mesmerizing cosmic collisions, the universe continues to captivate us with its infinite possibilities. In this riveting documentary, we have delved deep into the anomalies of the universe, shedding light on the extraordinary phenomena that defy our current understanding. We have witnessed the dance of galaxies, the birth and death of stars, and the awe-inspiring power of supernovae. We have explored the enigmatic nature of dark matter and the tantalizing secrets hidden within inner dust clouds. As our exploration draws to a close, we are left with a sense of awe and humility. The anomalies in the universe remind us that there is so much more to discover and understand. They challenge our existing knowledge and beckon us to push the boundaries of our understanding even further. So, let us continue to gaze at the stars and seek out anomalies that lie hidden in the depths of space. For it is in these moments of curiosity and wonder that we inch closer to unraveling the mysteries of the universe and perhaps, one day, find answers to the questions that have eluded us for centuries. Join us on this extraordinary journey of discovery as we embark on the next chapter of exploration and continue to unravel the anomalies that shape our universe.